Hi, this video is a complete guide to selection of fits and tolerance of a bearing shaft and housing seat, plus what GD&T controls and surface finish should apply over the bearing seats. And everything is well chaptered in timestamps, so later on you can visit to any specific chapter as per your need. But if you are watching this video for first time, I would recommend you to watch this full video at least once, because this is too much researched and experienced based video to give you a deeper understanding on bearing fitments, which is enough to make you a bearing fitment specialist. So in beginning of my design career, when I was a fresher, yes, I was also a fresher once upon a time, and I was so much confused about bearing fitment, that what fit or what exact tolerance should apply over the bearing seats, on the shaft and in the housing. Also, how the bearing should be fitted in an interference fit or a clearance fit. If the bearing should be fitted with interference fit, means a press fit or tight fit, then which ring should be interference fit? Inner ring or the outer ring or both of the rings? Or if the bearing should have clearance fit, means a slide fit, then which ring should be slide fitted? Inner ring or outer ring or the both of the ring? What is the magical combination of the fits for a bearing rings? So I asked my seniors, they were experienced design engineer. So one of my seniors suggested me to apply K6 fit on bearing shaft seat and H7 fit on bearing housing seat. And if we will have a defined fit, then we can specify the tolerance as well for that size. In a CAD drawing environment, something like this, very simple. But if you are making your drawing manually, then you can check the fit tolerance table, ISO 286, link is in the video description. In this table, we can find the tolerance of the size for a defined fit, something like this. So I became clear, no more confusion. I was confidently defining the same one magical fits for every bearing fitments. K6 on the shaft seat and H7 in housing seat. But my confidence didn't last long. When I changed my job in different companies one after another, I meet lots of design engineers and they suggested me different fits for the bearing fitment, not that same magical fit. For bearing shaft seat, someone suggested M6, someone suggested G6. And for the housing, someone suggested H8 and someone suggested P7. Someone suggests direct tolerance like 5 to 10 micron of interference should be on the bearing seats. So consider the seat tolerance accordingly. So the bearing fitment become more confusing for me, a mystery for me. And whenever I ask them that how you are suggesting these fits, what are the basis of selecting the right fits for a bearing, then mostly they said the fit what I'm suggesting you is my senior suggested me. And someone said that they have seen that fits in Japanese manufacturing drawing. And Japanese are always, So I stopped asking anyone and I start my own research. That is there any formula or a standard recommendation for selecting of right fit and tolerance for a bearing seat? So after so much research, after a year, I stumbled on a bearing technical data sheet. For example, this is deep groove ball bearing 6204 technical data sheet from SKF. In this data sheet, every parameters of the bearing are defined, like bearing bore size, bearing outer diameter, but without any tolerance. And then bearing load ratings, bearing limiting speeds, bearing different properties, bearing technical drawings like solder dimensions and other dimension. And then again more specific sophisticated technical data like fatigue load limits. But there was nothing much about bearing fitment. Then my eyes stumbled on bearing tolerance class, the dimensional class P6 and radial runout P5. So the thought came to my mind that this dimensional tolerance class P6 is something which might help me in selecting of right fit for a bearing. So I researched further and get to the P6 tolerance class for radial bearing. So this comes out as a table the table of dimensional tolerance of bearing inner ring and the outer ring, and also the tolerance for the bearing width. For example, as this 6205 bearing inner ring diameter is 20 mm, so according to this table, the inner ring 20 mm will be fall between 18 to 30 mm range. But if you are seeing this table for first time, there is so much data. But for the bearings which has a cylindrical inner ring, the most of bearing we use has cylindrical inner ring and outer ring, not the taper ring, then we have to only see this delta DMP, not all this data. These data are for taper bearing series. So for this row, delta DPM upper limit is 0 and lower limit is -8 micron. Means as this 6204 bearing is manufactured in P6 dimensional class, so its inner ring tolerance will be 20 plus 0 minus 0.008 mm. 1 micron equal to 1 divided by 1000 millimeter. And for bearing outer ring of 27 mm diameter of this bearing will fall between 30 to 50 mm range, 0 to -9 micron. So the bearing outer ring will 47 plus 0 minus 0.009 mm. Now this P6 is called as bearing precision grade. If you will go for more precise grades like P5 or P4, you will get more tighter tolerance. Like instead of -8 micron, you will get -6 micron for the same bearing size, for the same bearing ID. If you want to more understand about bearing precision grade, later on you can watch this video. But the main point is bearing precision grade do not define bearing fitment. It simply defines the size tolerance of the bearing, the size tolerance of the bearing inner ring and outer ring. But we are here for the size tolerance of bearing seats, the recommendation or the formula of the size tolerance or fit for the bearing seat, not for the size tolerance of the bearing itself. So why I have explained bearing precision grade and the bearing tolerance itself? Is this bearing precision grade, bearing size tolerance helps in determining the bearing seat size, the bearing seat size tolerance? So no, not directly. Bearing precision grade do not influence the selection of bearing fits. So further, after many years of research and experience, I finally came to understand that bearing fitment, bearing seat tolerance depends on many parameters. Actually, mainly 6 parameters in a standard case. Number 1 is which bearing ring is rotating, inner ring or the outer ring. Number 2 is loading condition, rotating load or stationary load or vibratory load. Number 3 is amount of the load, light, normal or heavy load. Number 4 is the size of bearing, bore size of the bearing. Number 5 is the design and the material of the bearing seat, cylindrical seat or a hollow seat or a taper seat. And number 6 is the type of bearing, ball bearings or roller bearings or other types of bearing. But bearing fitment do not depends on bearing precision grade, bearing tolerance class. So why I even explained bearing precision grade at the first place? So the bearing precision grade dictates required geometric tolerance of the bearing seat, total runout of the bearing seat, plus required surface finish of the bearing seat. Yes, this is a very important thing that we have to understand, that bearing fitment is not only about the selecting the right fit, the dimensional tolerance. We will have to also control the geometric tolerance of the bearing seat, total runout of the bearing seat, and the required surface finish of the bearing seat. Because the bearing seat is a very crucial surface and it has a significant effect on bearing performance and the bearing life. So let's first deeply understand bearing seat itself. And then we will go for selection of fit and tolerance of the bearing seat, and then total runout of the bearing seat, and also why we should control the total runout of a bearing seat, and then how to select the surface finish for a bearing seat. So what is a bearing seat? So let's say this is a complete shaft, okay? But this shaft step is called bearing seat. Yeah, in housing as well, this housing step is a bearing seat. A bearing seat is a specific area, mostly cylindrical surface, where a bearing is positioned or installed. Very simple. But a bearing seat can be tapered surface also for a taper ring bearing, or a flat surface also for a thrust bearing like this one. And there are three main functions of a bearing seat. And there are three main functions of a bearing seat. Number one is support the bearing rings against the load. Number two is prevent the bearing ring from slipping against high rotational speed under heavy loads. And number three is correct the positioning of rotating axis of the bearing rings to achieve the overall bearing running accuracy. Now, as a design engineers, we often racing against project deadlines, and we always try to find the perfect standard items for our design. And often we end up using multiple standard items from multiple suppliers, and their delivery time and cost do not align with our projects. So here is the solution. Introducing JLCMC, our today video sponsor, the one-stop solution for the engineers and makers. JLCMC offers an extensive range of high-quality mechatronics parts, including rotary and linear motion parts, all the hardwares, caster wheels to tiny mechanical components like springs, magnet, position pins, all types of fastener, pneumatics, and their electronics part, everything you need all in one place. So whether you are doing a serious industrial project or a DIY application, or especially a special purpose machine designing, JLCMC has it all. Also, no worry about quality. All the components qualities are as per the industrial standard at very economical price. Also, no matter where you are living in this world, JLCMC has fast and stable delivery system all around the world. Will deliver to your doorstep. Plus, as a design engineer, we always need 3D model of every components for our design. So download the 3D models directly from the site with very simple registration. So do check out the JLCMC website, link is in description. And now let's back to our main topic. So let's start from number one. So to fully exploit the load carrying ability of a bearing, our bearing seat must support the both rings of the bearing around the full circumference and across the entire width of the rings. Therefore, the bearing seat to be manufactured to adequate geometric and dimensional tolerances. Plus, the bearing seat should not be interrupted by a groove or a hole or other features. Do not add any undercut or slot or anything over the bearing seat. Bearing can be permanently damaged under heavy loads. Now, the second main function of a bearing seat is prevent the bearing rings from slipping. If the bearing rings will be slip over the seat, it can lead to fretting corrosion and eventually wear. Fretting corrosion looks like this. I don't know how to define this, but you have must seen it in somewhere, maybe in old machineries bearing seats. Fretting degrades the surface and reduces the fatigue strength of a material of a steel. And sometimes slipping off the ring can result in permanently wear of the bearing seat and the bearing ring itself, something like this. So to prevent this from happening, an adequate and enough interference should be between the seat and the bearing rings. But maintaining an interference fit on the both rings, inner ring and the outer ring, is problematic. Assembly and disassembly of the bearing will be difficult. Also, the bearing could be potentially damaged during the assembly and disassembly of the bearing. Because let's suppose if the both rings have interference fit, and I want to first assemble the bearing inner ring over the shaft seat, then I will have to hard press on the bearing inner ring if bearing both rings are interference with the seat. And as the bearing outer ring is also interference with the housing seat, so the bearing will goes under stress, kind of shear stress, something like this. Same, if I will try to first press the outer ring, then inner ring will be resist the movement because of shaft interference, and again bearing will be goes under heavy stress during the assembly, also during the disassembly. And this stress can potentially damage the bearing or disturb the bearing internal clearance, which will reduce the bearing life as well as bearing running accuracy for sure. So what we usually do for a general application, we keep one ring in interference fit and one ring in clearance fit. But where we should keep which ring in interference fit and which ring in clearance fit is depends on two main factors. One is which bearing ring is rotating, inner ring or the outer ring. And the second is condition of direction of load over the bearing, rotating load or constant direction load. And on the basis of these factors, there can be four possible operating conditions. And the recommendation is the bearing ring which has a relative motion with the direction of the load must be interference fit. Means there will be a higher chance of the slip, whether the direction of load is constant or rotating. And the bearing ring which do not has a relative motion with the direction of load, that has to be slide fit, means there will be a less chance of the slip. What does mean? So in this first operating condition, this is a bearing block where block is fixed and a rotating shaft is inside the bearing inner ring. So the inner ring is rotating and outer ring is stationary. And as the load direction is constant direction load means the load which do not change its direction during the rotation. For example, let's say this shaft has no unbalanced mass. So the direction of the load of this shaft is constant over the bearing, which is gravitational load towards downward, no matter how much rotating speed of the shaft is. So in this condition, the direction of load is in relative motion with the bearing inner ring, because the direction of the load is not rotating with the inner ring. The direction of the load is constant downward, but the inner ring is rotating. So the inner ring should have interference fit. And as the outer ring is not rotating, means there is no relative motion between the direction of the load and rotation of the outer ring. So we can keep the outer ring with a clearance fit. Now in the second condition, this is the same bearing block where the bearing is fixed and a rotating shaft is inside the bearing inner ring. So the inner ring is rotating and outer ring is stationary, but the direction of load is not constant. The load is rotating. Rotating load means the load which oscillates, change its direction with the rotation. Like an unbalanced mass on this rotating shaft is applying an rotating load over the bearing. Also, for example, load acting on connecting rod bearings are considered as a rotating load. So in this condition, the direction of load is in relative motion with the outer ring, not with the inner ring, because inner ring is also rotating. So in this case, the outer ring should be interference fitted. And we can keep the inner ring clearance fitted. Interesting, isn't it? And in this third condition, now the outer ring is rotating and inner ring is stationary and the direction of the load is constant. For this condition, we can imagine a skating board. The bearing outer ring is rotating and inner ring is fixed. And the direction of load is constant towards downward, the load of the person. So in this condition, the outer ring is in relative motion with the direction of load. So the outer ring should be interference fit and inner ring should be clearance fitted. If you do a skating, please let me know what combination of fits you are using over the bearing in a skating board. Now, in this last condition, the outer ring is rotating, but the load is also rotating with the outer ring. Means now the inner ring has a relative motion with the direction of the load. So in this case, the bearing inner ring should be interference fit and the outer ring should be clearance fitted. Now, look, this seems complicated, but this is very simple. You don't have to memorize this table. The bearing ring, either inner ring or the outer ring, the ring which has in relative motion with the direction of load, either rotating load or the constant load, the ring should be interference fit. And another ring clearance fit is possible. I hope it's clear to you. Now, in some cases, direction of load could be indeterminate, undefined, like vibration, sudden load peaks, or unbalanced load in high-speed application, where we cannot accurately describe the direction of load. So in these conditions, particularly where a heavy load are involved, there will be a higher chance of bearing ring slipping. So we should use interference fit on the both rings of the bearing. So in this case, for easy installation, we should use separable ring bearings like cylindrical roller bearings or needle roller bearings or cartwheel bearings. These bearing rings can be mounted with interference fit on the both rings. Or we can use taper ring bearings. For example, in tractor front axle wheel, a tapered roller bearing is used. Now, there are some also special cases, like in application where high precision is required, like a CNC machines. So in this condition, we actually preload the bearing by interference fit. But preloading is a different topic. For that, you can watch this video. Now, the bearing fitment also depends on material of the shaft and housing. The shaft and housing made of other materials than steel or cast iron may require different fits. The fit will depend on its properties, the strength of the material and thermal property of the material. Also, in some cases where bearing ring is normally reach a high temperature, so in this case a different fit will be required. Also, in some cases where application is subjected to repeat start and stop, so in these cases both ring may require interference fit. So I hope you are pretty much clear that where we should use interference fit and where we could use clearance fit. And now let's see that how much interference fit or clearance fit is needed for a bearing seat. So this is a formula to estimate the required interference of a bearing with seat. So where the delta is required interference in micron, Fr is a radial load in kilonewton. So if the load will be heavier, the required interference will be large. D is the bearing bore diameter and B is the width of the bearing. But you don't have to calculate or memorize this formula. In general, we should prefer recommended fits table. This table are from SKF bearing. You can download it from video description and save it in your PC or take a printout because you are going to use this table several times. So this table number 5 is for shaft seat, for radial bearings and solid steel shaft seat. And this table number 8 is for housing seat, for radial ball bearing and steel housing seat. Likewise, there are tables for the roller bearings, table number 6, for the thrust bearing, table number 9, and tapered sleeve, table number 10. In this video, I will only explain for the ball bearings because procedure are the same for other types of bearing. So this table is for shaft seat. And at this moment, let's only focus on dimensional tolerance. So if the condition is rotating inner ring load, means the direction of load is in relative motion with the inner ring. Operating condition number 1 and 4th. Here don't be confused with rotating inner ring load means inner ring is rotating. Here inner ring is stationary but the load is rotating. So the direction of the load and inner ring has a relative motion. So it's called rotating inner ring load. I hope You got my point. Just keep in mind relative motion. So in this condition, we will select the fit from here as per the amount of the load and inner diameter of the bearing. If the load is light, means the load of our bearing is less than 0.05 times of bearing dynamic load rating C, then select from these rows as per the size of bearing inner ring. If the load is normal to heavy, 0.05 times C to 0.1 times C, then from these rows. And this all will give you an interference fit. And if the load is too much heavy, then we can use this formula. That would be a special case. And now for stationary inner ring load, means operating condition number 2 and 3, where the direction of load is not in relative motion with the bearing inner ring. Either bearing inner ring and the direction of load are both rotating or the both are stationary. Then choose from these bottom rows. G6 if easy axial displacement of inner ring on the shaft is desired, and H6 if the displacement of the inner ring on the shaft is unnecessary. Both are clearance fit. Same for the outer ring. If the outer ring having relative motion with the direction of load, choose from bottom rows. If the outer ring having relative motion with the direction of the load, choose from top rows. This is for the rotating load and this is for the direction of load is undefined, undeterminate. This all are interference fit. So let's understand it with an example. Let's say we have these two simple bearing block with 6204 deep groove ball bearings. And a heavy shaft is there. The mass of the shaft is, let's say, 200 kg. Means 100 kg is over each bearings. And a motor is connected and rotating this shaft. So what will be the fits over the bearing seats, over the shaft and in the housing of the bearing block? So step 1 is understanding the operating condition. So the bearing inner ring is rotating and outer ring is stationary. And as there is no unbalanced mass over the shaft, so the direction of load is constant. Gravity load towards downward. In this table, the same as this first condition, rotating inner ring load and stationary outer ring load. Because the direction of load is in relative motion with the inner ring. So our first thought is the bearing inner ring to be interference fit and the outer ring to be clearance fit. Now the second step is know your load. So the applied load is 100 kg over one bearing. So convert it into kilonewton because bearing dynamic load rating C will be always in kilonewton, 13.5 kilonewton. So 100 kg means 1000 newton, approximate means 1 kilonewton. Now write this load P in terms of dynamic load rating C. So divide the load P with dynamic load rating C, 1 divided by 13.5. So it will 0.074 means P is equal to 0.074 C. And now refer to the recommended fit table for the shaft seat, table number 5. So first choose the right condition. And our condition is this first one, rotating inner ring load. Right here, rotating inner ring load. And our load is normal to heavy, 0.074 C will lie between 0.05 C to 0.1 C. And our bearing 6204 inner ring diameter is 20 mm. So this will lie in this row, 17 to 100 mm. Recommended fit for the bearing seat on the shaft is K5. And if we will apply this fit over the 20 mm shaft seat, tolerance will be plus 0.002 to plus 0.011. And as the bearing inner ring tolerance is 0 to minus 0.008 mm as per the bearing precision grade P6, so this will definitely an interference fit. I hope now this is so much clear to you. Now let's select the fit for the housing seat, table number 8. So the load of our bearing outer ring is a stationary outer ring load. And in this table, for all kinds of load, we can select H7, and for light to normal load, P less than 0.1 C, with simple working condition, we can select H8. H8 is little loose fit as compared to H7. So as our application is very simple working, so we can go for H8. So for the housing seat diameter 47 mm, H8 fit tolerance is 0 to plus 0.039 mm. And as the bearing inner ring tolerance is 0 to 0.009 mm as per the bearing precision grade P6, so this will definitely a clearance fit. So this was all about selection of fits for the bearing seats. So just for a quick recap, the first is know your operating condition, which ring to be interference fit and which ring to be clearance fit. Second, know your loads as compared to bearing basic dynamic load rating, light load, normal load or heavy load. And then accordingly select the recommended fit from the table. But keep in mind, this is for a standard operating condition for a ball bearing. For other bearings, there are also separate tables for them. And now the third main function of a bearing seat is the bearing seat must accurately position the bearing rotating axis to ensure the bearing operates with minimal run out and maximum precision. Because let's say we have a very precise motion application, let's say a CNC machinist spindle. And for high precision motion, I have used a super precision grade bearings, a very expensive bearing. Super precision grade bearings means the bearing dimensional class below P4, means high dimensional accuracy as well as high running accuracy. High running accuracy means high concentricity precision between the bearing rings. But if my bearing seat geometric tolerance is not precise, then I cannot achieve the overall precision. So the bearing seat geometric tolerance also must be precise. And in case of bearings, as bearings rotates around their axis, we controls bearing total runout as per the bearing precision grade. And this is the table. This is for the shaft seat and this is for the housing seat. This row is for normal grade bearings. This is for P6 grade and this is for P5. For example, as 6204 bearing precision grade is P6, so this will fall in these rows. Radial runout IT4 by 2, axial runout IT4, and for the housing IT5 by 2, total radial runout, and IT5 for the axial runout. So if you are wondering what is IT, so IT is tolerance grade, international tolerance grade. Like in fits H7, 7 is IT grade. In G6, 6 is IT grade. So for IT grades, we can refer this table, ISO 286 table 1. So for IT4 for 20 mm diameter, 20 mm will fall between 18 to 30 mm, it's 6 micron. And IT5 for 47 mm diameter, 47 will fall between 30 to 50 is 11 micron. IT4 by 2 means 3 micron, IT5 by 2 means 6.5 micron. So to apply the GD&T controls, we define shaft seat as a datum, datum A and datum B. And I will define the shaft radial total runout 0.003 and axial total runout 0.006. With respect to A-B, A-B means both datums have equal priority. And likewise, we can also define the total runout over the housing seats, something like this. And now it's time to define the surface texture of the bearing seats, surface finish of the bearing seat. So the surface finish of a bearing seat has a less impact on bearing performance if we will compare with the dimensional and geometrical tolerance of the seat. However, a smooth surface reduces the interference force during the assembly. So for the surface finish, we refer this table. We can choose the surface finish as per the tolerance grade. Or we can also choose from this table. So as our load was normal to heavy and the shaft diameter was 20 mm, so in this rows the surface finish RA is 0.4 micron and for the housing is RA 3.2 micron. So we can apply RA 0.4 over the shaft seat and RA 3.2 over the housing seat, something like this. So this was all about the bearing fitment, bearing seats, selection of fits and tolerance for the bearing seat, also the run out control for the bearing seats and the surface finish of the bearing seat. And I hope this video helped you. If it did, please give us a like and thank you so much for watching this video.